Okay, we welcome everybody to a Wolfram Physics Project working session. Jonathan and I have all kinds of things to talk about, so we might just start talking about some things and we'll see where this goes. So Jonathan has been working hard on kind of a new generation of numerical methods for general relativity, among other things. And we think that there's a potential generalization of that to new methods for solving PDEs in general. We can talk a little bit about that. I've been working on non-deterministic Turing machines, which seems like an obscure corner topic, but which I think is relevant to questions like consciousness, bizarrely enough. We might talk a bit about that. This morning, we happen to be talking about proof-assistant systems and the formalization of mathematics. I don't know where we should start here. Should we start on the proof assistant stuff, just because it's recent? You know, the main thing, I guess, the question there would be about, well, you were just saying that you know, the thing you were showing was an implementation of, I don't quite understand the hierarchy of things that proof assistants can do and the relationship of different kinds of type theory. So maybe you can you give a bit of a discussion about that?
Yeah, okay, sure. So there's so the general thing that lots of proof assistants like Coq and Lean and other things that are based on sort of type theory. So Isabelle and Hall are a bit different. They're based on this program of computable functions, this library of computable functions set up. But so at least the ones that are based on type theory, they are all based around this thing called the calculus of constructions, where the idea is it's making use of a generalization of the Curry-Howard isomorphism. So the Curry-Howard isomorphism is saying, okay, if you have a statement in intuitionistic propositional logic, then you can construct an analogous term in a simply typed lambda calculus, and vice versa. So that there's some fundamental correspondence between terms in intuitionistic propositional logic and terms in simply typed lambda calculus. Turns out you can go one step higher than that, because theorem proving over propositional logic is not particularly interesting. You know, SAT solvers and things can do that rather trivially. So the place where it gets more interesting is when you can do predicate logic. And so therefore when you can handle quantification. And so that's what this calculus of constructive types does. Or calculus of constructions does. It says, so we abstract the Curry-Howard isomorphism one level up, and we say, so now there's a correspondence between propositions in intuitionistic predicate logic, you know, including universal and existential quantification, and terms in some higher order some higher order typed lambda calculus. And so that's the essential starting point. And then there's, as you say, there's this hierarchy of type theories. You can, you know, depending on if you allow for types to build other types, you allow for type constructors, then you go from ordinary type theory to inductive type theory. If you also allow types to depend on values, which lets you essentially describe universal and existential quantification through type constructors, then you're into dependent type theory. If you also introduce notions of propositional equivalence, then you're now into homotopy type theory, and so on. So those are all higher level objects, but the basic idea of calculus of constructions is the lowest level thing.
But so I'm still trying to understand this. So at some level, the fundamental operations we believe to exist are, you know, essentially pattern matching and substitution. That seems to be that is both in our model of physics and in the way that Wolfram language works and a bunch of other things. Sort of the lowest level, apparently inevitable kinds of operations are this thing matches that, and you can substitute this piece for that piece. Is that a fair? And
right.
then what this is doing is saying, you know, the Curry-Howard, you know, correspondence and so on are saying with those operations alone, you can build up a bunch of known mathematical kinds of constructs, like propositional calculus, for example.
Right. And in the most general case, it's saying that they're the same, that pattern matching and replacement are, you know, in as much as they define a model of lambda calculus, they are mathematics up to some isomorphism.
Yeah, but that's, like a lot of computational things, that's essentially a statement of compilation. That is, given, with these underlying, with this underlying set of operations of pattern matching and substitution, you can then build up from that these things that you identify as being things like and or. I mean, it's not that, and or are just names you give to these combinations of substitution and pattern matching operations. You say that's like an and, that's like an or.
Right. But I mean, at some level, this distinction that we're making between the purely symbolic and or and the models of and or in terms of lambda calculus is related to this distinction between constructivist and non-constructivist foundations for mathematics, right? So we can define and or purely axiomatically without ever giving an explicit model for what they really mean, how to actually them. And what the Curry-Howard isomorphism is telling you is that actually it is possible, for the kinds of objects that you discuss in ordinary mathematics, it is possible for you can do better than just defining a purely axiomatic symbolic description. You can actually compile them into something computational, which therefore allows for proof validation and things like that.
Right, but by computational, what we mean is pattern matching and substitution.
Sure, yes.
I mean, that's not totally obvious. I mean, that should be considered the foundation for everything is what I, for example, have implicitly assumed for most of my life, so to speak, but it doesn't mean it's totally obvious.
But that's why that's what lambda calculus is all about, right? You've got beta reduction, which is pattern matching, and you've got alpha conversion, which is substitution.
Sure, right. It's what combinators were like too. I mean, that was kind of the combinator idea, which was then taken by lambda calculus, et cetera, et cetera, et cetera. And I don't, in a sense, I mean, it seems like a self-evident idea. One is always suspicious about self-evident ideas, but it seems like a self-evident idea that it's just you match. I mean, by the way, we know, of course, that the matching and reduction thing in the presence of variables is a bit more complicated. But let's ignore that point. I'm just trying to understand the logical flow. So we're starting off sort of the lowest level thing that we believe is the foundation for both physics and mathematics is essentially matching and substitution of symbolic things, right? So now we're saying that on top of that, you're building. So you can think of that. The question is, how do you build a mathematical structure on top of that? How do you build named things? You've got that underlying sort of infrastructure, and now you want to construct things that you actually give names to and that are identifiable in some useful way as being mathematical concepts.
Right.
Yes. And you also say you can do the backwards thing that is kind of like what Euclid, in a sense, did, which is to say, just consider these axioms. We don't say, I mean, it's the implication of Euclid, but it's more like what Peano and people like that did, was just consider these axioms. We don't know whether they're implementable in terms of something lower level like substitution and pattern matching. And that's kind of the non-constructive, that's the idea of just pure axiomatic mathematics without any grounding in something constructible.
Right. And I mean, this is subject to one's own personal view on the philosophy of mathematics. I would argue that the purely axiomatic approach is a naive kind of pre-Gödelian approach, right? It doesn't appreciate, it doesn't take the idea of computational irreducibility seriously. A bit like with category theory and its, instant morphism composition without treatment of irreducibility. The idea that you can just axiomatically define equivalences between things elides a lot of subtlety about the details of that computation, which I think we should no longer be eliding. We should. Yeah,
right. Well, historically, perhaps the reason that happened was that people. Well, let's understand a little bit of that history, right? How do we get to the point where people just said, "Let this be true," and let's not worry about the things underneath, the things that are represented by these things which we just say are true. I mean, because the origin of most of this kind of axiomatic approach to mathematics was Euclid, and I think one of the issues is, with the parallel lines business and things like that, is to say people got afraid of the idea of actually just draw the lines and see what happens, because they discovered that it was, well, I'm trying to think how this really, because I agree that this was a phenomenon of the late 1800s, was this idea of just write down these axioms and assume that you can build things just on the basis of not on some sort of constructible computational basis.
Right. Right. Actually, can I give at least a concrete example of a place where that gets one into a very complicated philosophical mess?
Yeah.
Which is in formulation models of the real numbers, models of the continuum. So you can write down a set of axioms. I mean, because the real numbers, they are basically just defined. You can write them down axiomatically in terms of there's an order relation that allows you to compare real numbers, and there are some algebraic properties that say you can add them, multiply them, and so on. But then, in the late 19th century, particularly with people like Dedekind, there was this idea that you could do better than that. You could give explicit constructions of the reals. And so there are a whole variety. There's things like, so Dedekind cuts are a famous example where you treat each real number as a partition of the rationals into two sets, or Cauchy sequences where you treat essentially the real numbers as being the metric space completion of the rational numbers, or there are continued fraction ways of constructing reals, and all these different kind of algorithmic procedures for how you construct a real number. But actually, it's very, very non-trivial to say, if you ask the question, are the Dedekind reals the same as the Cauchy reals, and are those the same as the continued fraction reals? They all obey the same axiomatic properties, but it's very, very hard to say whether they're really modeling the same object, because essentially because of Gödel's theorem, because no such axiomatization is ever going to be able to define in a complete and consistent way what the real numbers really are. And so there's a huge amount of ambiguity and so there are models in which you can construct Dedekind reals, but you can't construct Cauchy reals. And there are models where, one has a slightly different module structure over the field of rationals to a different model of the continuum and things. And it all becomes a big mess unless you start from an explicitly constructivist foundation.
Yes, but I mean, well, this question of whether the real numbers exist and so on as a whole, I mean, yeah, right. I mean, the problem is, yes, this idea of just introducing mathematical concepts, and I've always viewed it as being, you define something by its constraints is a really weird way to work. I mean, it's a very certainly in my way of thinking about things, it's always so. But by the way, the same has happened in physics. Einstein's equations, as an example, are a definition of space-time by constraints. Right? They're not a sort of constructive story of what space-time is like. They are a story of, these are constraints that space-time satisfies.
I'd argue all theories of physics before our model have had the feature of being non-constructive.
Is that a true statement?
At least I don't know of a counterexample.
Well, I mean, it depends what you mean. I mean, for example, the quark model of hadrons is in a sense a thing which says you can build up hadrons from quarks. Right? I mean, in other words, it's not just saying there exists part of the issue is.
But maybe I'm very naive, but is that not based on some, isn't there some implicit axiomatic foundation in QFT or something for that model?
Not really. I mean, yes, you could claim that, but not really. I mean, it's like saying all material objects are made of atoms, which is again, in a sense, a more. I mean, look, that was the thing. I mean, I suppose in some sense the Newton story was the beginning of this story of just saying, it satisfies a differential equation, and then that's what happens. But look, in terms of, okay, so coming back to the question of, okay, so one question is, when you have a result in mathematics, which seems to be non-constructive, what does that mean in terms of, so you have some claim, I don't know, I don't know many of them. This Banach-Tarski thing is an example of one that's often quoted, right? And you have a claim, and there is claimed to be, do we ever know that there can be no constructive proof of something? Or does that not even make any sense? In other words,
we can know that. I mean, so for instance, to take maybe a slightly more, I mean, it's related to the Banach-Tarski thing, but it's a slightly more down-to-earth example, the existence of non-measurable sets. So you can prove in ZF without choice, you can prove that non-measurable sets do not exist. Whereas we can also prove that with choice they can exist. And so the existence of non-measurable sets is an example of something for which there is no constructive proof, because we can show that in the constructive foundation they actually don't exist.
Fine, but I mean, the fact that there's no constructive proof just means it happens to be a random fact that's independent of those particular axioms. I mean, why is that?
Yeah, sure. I mean, I
mean, there are tons of random facts that are independent of any particular set of axioms. I mean, right. I suppose the big surprise of mathematics, as we practice it so far, is that when we set up these, necessarily inadequate axioms for number theory, that most things we seem to care about proving are not independent of those axioms. That's the non-trivial fact. Not that that we did, decently well with those axioms at capturing the things we need to capture to be able to prove the things we care about proving.
Which I take as evidence that mathematicians follow some kind of action principle.
Well, yes. I mean, I think or I'm not sure about that, but I mean, well, okay, let's go through that. So, I mean, from a given set of axioms, we certainly know that. So there are two ways we can think about mathematics, and maybe this is, one way is this sort of proof theoretic way where we're just following this multi-way system of, proving all the things we can prove given the axioms we've defined. And that gives us a certain set of things. Now there's the question of if underlying the things about which the axioms are stated, there is some sort of fundamental mathematical, fundamental sort of computational infrastructure, then there may be things that will be true, quotes in mathematics terms, in a particular model, which will not be provable from that axiom system. So how should we think about that? What is our minimal case where we have both this is an interesting question. So what's the minimal case where we have both a reasonable computational infrastructure and a set of axioms? So for example, with Turing machines, you don't usually talk about Turing machines in terms of axiom systems. You usually talk about them in terms of just here's what they do. So where's a case where we have both sides coming together, where we both have a computational model of what's going on and an axiomatic model, and where we can see the interplay between those?
Well, I think something like the natural numbers in constructive set theory would be, maybe it's not the cleanest example, but it's at least an example, right? That you can define the operations of set theory purely algorithmically, and you can construct the natural numbers purely set theoretically, and so then all the operations on natural numbers then have some immediate algorithmic interpretation.
Yeah, okay, but it's a more complicated. I mean, is there a more down-to-earth version of that? So, for example, I mean, in algebraic theories, we typically have the particular group versus the things true of all possible groups. Right. And that's the difference between the particular group is saying, you can. I mean, so what would be an example of a thing where?
I mean, universal algebra is hard to make constructive.
What do you mean? I mean, you mean general universal algebra? I mean, there are many particular theories of universal algebra, many particular models of universal algebra, which are, I think, count as. I mean, you're just saying. Well, I mean, I see. So you're saying, like, if we're doing group theory and we have these two words in a group, knowing whether those two words are the same is something that can be arbitrarily difficult. So is that what you mean?
What I'm saying? No, I mean, universal algebra is not talking about a group, right? Universal algebra is talking about statements that are true of all groups.
Sure.
The point is, for any given group, yes, absolutely, you can make it constructive because you can define an algorithm that solves the word problem and stuff like that. But actually, the space, reasoning about the space of all possible algebraic structures of a particular type, it's hard to construct an algorithmic interpretation of that. Well,
right. I mean, yes, we don't know one. I mean, that's not one that we usually talk about.
Right. That's what I'm saying. So universal. So you were talking about proving things about, or you were talking about general axioms of group theory, and I'm pointing out that the constructive models of particular groups are easy to produce, but constructive models of universal algebra.
All right. So where do these things intersect? Right. So there are things where we have models that are natural and where we have kind of whole axiomatic systems that are natural. And in the case of in the case of arithmetic, for example, we have the there it seems quite natural on both sides. We have the integers on one side, we have the Peano axioms on the other side. They're both reasonably natural, but it's a very complicated setup. So the question is there a simpler setup like that, perhaps with string systems or something, string rewrites, something like that, where we can see both sides of that story, where we can both see, okay, so in the case of the string systems, for example, there are things that we played with sort of valuations of strings, where you have the string rewrite system, which defines, which has a bunch of axioms that say how to rewrite the strings. And then we also have this idea that strings have a value, numerical value, and then that's a particular model of the strings. But again, it doesn't seem particularly natural.
I don't see why you need the numerical value. I mean, the strings themselves are concrete objects, right? So semigroups, which are basically what you're talking about here, are a good example of something where there is an obvious intersection, right? Strings are a concrete thing. You can do concatenation. You can define algorithmically what the concatenation operation does, etc. And you can also write down the associativity and identity axioms for that semigroup.
No, but. Well, okay, maybe I'm not making my point very well. I mean, the issue here is there is a certain set of things that when you talk about non-constructive proofs, the question is, what is the most simple-minded case? Okay, for example, for string systems, what will be a non-constructive proof in a string system?
Well, but this is my point, right? That if you have a monoid structure, it's quite easy to make it constructive. String concatenation operations are.
Okay, so what is so give me the most simple-minded system that would have something non-constructive.
No, so if you had a string system which was augmented, say, by a notion of double negation, so you could effectively do proofs by contradiction in the string system, then you would have a shot at having something non-constructive.
What on earth is so? I mean, I played with ages ago in string systems. Just the string has A's and B's in it, and negation is interchange A and B.
Right. So like you did in it was at chapter 11, the principle of computational equivalence chapter of NKS, right? You had those multi-way systems with with sort of black and white cells or zeros and ones in them, and use them to kind of investigate consistency and completeness by just comparing
right.
Numbers of strings of a particular type. So if you had a system like that, then you could start. Then you can have the situation, and so you have a negation operation. So as well as the concatenation operation, you have a negation operation. Then you can start to make statements like, there does not exist a path between these two strings, which you can prove, which you might be able to prove without actually witnessing that path, right? Because you could take the statement that the path exists and then negate it.
How would I take a statement in that setup? How would I formulate the statement that path exists?
Well, yeah, I mean, you would have to have some way of expressing statements about paths from within the string system itself.
Right.
Which
right there is somewhat non-trivial. I mean, that's a Gödel-like construction.
Yeah, but as soon as you have that situation, and then you can, so if you wrote the statement, there exists a path between these two strings in the string language, and then just negated all the characters, and you found a proof of that in the string system, then you would have found a non-constructive proof that there does not exist a path between the original two strings, because you proved it to be true subject to the axioms of the string system, but you haven't actually witnessed the path.
Right, but this requires that you have some kind of meta. You are able to represent in the string system statements about itself.
Right.
Which is already quite non-trivial. That's a non-trivial piece of compilation that we haven't done for string systems.
Right.
And which, by the way, for these simple systems, that is like universality proofs, and they're always horribly messy.
Yes.
Right. So, I mean, the question here is.
I mean, it's worth saying this argument has exactly the same structure as universality proof. It's a diagonalization argument of exactly the kind that you would use in, proving undecidability of the halting problem or something.
Right. And, another interesting fact is this very fact that the universality proofs are complicated. I mean, what does that tell you? It probably tells you something about the fact that What does it tell you? In these systems, I mean, so one of the things surprising about certain kinds of systems is, the surprising fact about number theory is that it's doable. The surprising fact about number theory is that it is not the case that most number theoretic questions that people ask end up being undecidable.
Right.
And that, in a sense, is surprising. And yet it's the case in these computational systems that a large fraction of questions you might ask do turn out to be undecidable. It's not the case that number theory is particularly easy to do universal computation in. Gödel's construction is messy. It's not trivial to encode, mathematical statements in number theory. So I don't quite know where, the question is, what is the intuitive thing that we get from the fact that universality proofs are hard?
Well, from my perspective, all it's telling us, I think, is that universality proofs are not, statements of universality do not correspond to the kinds of statements that mathematics, if left to its own devices, would otherwise prove.
Well, it's true, but it's also, they're not the kinds of statements that, so the issue is, so what you're saying is when we do a universality proof for a J-random Turing machine, for example, that we are using the tools of mathematics to do that. And that were we to have other tools, there might be a different and easier way to make that proof. But given that we're using the tools of mathematics to make that proof, the proof is going to be messy because it's a poor match for what is natural to do in making deductions about Turing machines. Is that your claim?
So all I'm really saying is, in order to do a universality proof, you effectively have to either implicitly or explicitly write a compiler within the object language that you're doing the proof for, right? Yep. So it's a general statement of the form, if I wanted to write a compiler for the Wolfram, this is related to the conversation we just had. If I wanted to write a compiler for the Wolfram language within the Wolfram language, that would be a non-trivial piece of code. But I could imagine there would exist a different programming language that had been constructed specifically for that purpose, in which the code would be much simpler, right?
Right.
And so in general, writing a compiler for a given language, within the object language itself is going to be a non-trivial task.
How does this relate to change of reference frames in real space?
Well, to the extent that reference frames in real space are models of object languages, it's the same statement, right? It's telling us that
there's a finite speed of right, that it's difficult to make that transformation.
Yes, but also crucially, that distances are covariant with respect to transformation in Rulio reference frames.
What do you mean?
That the difficulty of a universality proof is not fixed, right? It's not an invariant quantity; it's a covariant quantity. It varies, in the same direction as when I make a parameterized transformation of object language, which is effectively saying that the difficulty of writing a compiler will change for a given language, will change when I modify which language I'm writing it in.
Well, okay, but the claim is, if it is true that doing universality proofs is in some sense always hard, what is that a statement of? That's not a statement that we learn from computational complexity theory. It's not a computational complexity-like statement. What is that statement? What kind of a thing is that statement? In other words, what it's saying is, given a, I just don't know what that, is it some statement related to computational irreducibility? What is that statement? And is that statement is there a form of computational complexity theory that basically is answering the question, how hard is it, in standard computational complexity theory, you're interested in, polynomial time reduction or something like that. You're interested in things where there is the compilation from one thing to another is bounded in some way. But for this case of where you're not taking a bound on the size of the problem, it's not obvious to me the intuitive fact that it's hard to make universality proofs. I've actually never really thought about what the implication of that intuitive fact is. I wonder whether it tells you something about.
I find it surprising that it's even possible. I mean, a lot of my intuition suggests that it should not be possible to prove universality of an object language from within the object language.
Well, remember, all you're proving is, you're proving, you're just making a connection to, so you're just making it, a change of frame in real space. You're just proving that it's equal to something, that it is as universal as something else.
Sure. But the fact that that sequence eventually, can be made to terminate on something like something that's axiomatically true, like the Church-Turing thesis. I don't know. I find it counterintuitive in the same way that I find bootstrapping in compilers counterintuitive. The fact that that can work at all is
but I think this is the statement. This is the principle of computational equivalence, that this could possibly work. I mean,
sure,
yeah,
I appreciate it's true. I'm just saying it doesn't gel with my intuition. That's all.
Right. Well, but it's basically saying, you go around in this space and, you might say there is, the best, the most sophisticated, computational system, but that's not true. They're all, so there are two possibilities. One is there is some kind of ordering and there is a best computational system. And the other is there isn't, they're all equal, which is what this is saying.
Right. By the way, I have to say that, so this statement about, it's surprising that it's possible to do natural number arithmetic or something. It strikes me as being extreme, when you start to think about it in terms of as just a multi-way system for possible propositions and thinking about proofs as geodesics in that space. It's very similar to say, or it seems to me at least very similar to saying, if you're at some point P in space-time, and we know because of the structure of the Einstein field equations, you're following a geodesic equation. But so that, there are uncountably infinitely many geodesics you could conceivably follow, the vast majority of which are infinite in length for a non-compact space-time. But the ones that you will follow will always be finite in length. And they will always be kind of comparatively easy to obtain given your current position in space-time. And you could say that's really surprising. Why is it that I, as a geodesic normal observer, are somehow avoiding getting caught on one of these infinite length geodesics? But of course, we know that it's not surprising at all because we're following a geodesic equation that follows the consequence of the fact that we're on an Einstein manifold. And I don't know, maybe this is too simple-minded a view, but my position is that if we think it is the case, so now that we have a purely computational way of formulating the proof of the Einstein field equations for the case of causal graphs, in terms of essentially computational irreducibility and boundedness of the ability to make reference frames, there's nothing to stop us from applying the same argument to multi-way systems for mathematics, which will therefore also presumably obey some appropriate generalization of a geodesic equation, in which case the statement that somehow mathematics tends to avoid undecidability, as far as I can tell, becomes a bit tautological.
No, wait. First of all, the statement that you avoid infinite length geodesics, is that the statement that everybody eventually falls into a black hole?
Well, in some appropriate limit, yes.
Right. So the infinite length geodesics are, within a universe that requires an infinite, a universe that can have infinite, that survives in infinite time, etc. Right?
Sure. Yeah.
What happens in a time-like singularity? What is that? What is the length of the geodesic if you fall into a time-like singularity?
Well, the geodesics have infinite length but zero extent, as in the number of geodesics reduces to 1.
Right, but nevertheless, it is the case. If the question is, do you ever get to a normal form? Do you ever get to something where time ends? The answer is no. In a time-like singularity, you don't get to something where time ends.
Right.
But your argument is, okay, so you're making the argument, in a typical universe, it's full of black holes, it's full of space-like singularities, and you, as an observer, will live only a finite time before you fall into a space-like singularity, unless you are in an infinite universe.
I don't even think you need to go to the level of black holes. The statement I'm making is much more elementary than that. It's, okay, I'm a geodesic normal observer. I'm at point P in my Lorentzian manifold. I want to get to point Q. I can see point Q. I want to get there. I can't actually see it, but I have some idea of where point Q is in space-time, and I want to get there. There are finite length paths that get me between P and Q, and there are infinite length paths that get me between P and Q. And in a non-compact manifold, the infinite paths vastly outnumber the finite ones, in much the same way as the undecidable propositions vastly outnumber the decidable ones in any universal model of, any universal formal foundation for mathematics. So, but the question of why is it that I always follow the finite path, I never get caught on one of these infinite paths between P and Q, is a question about, am I obeying a geodesic equation or am I doing something else?
Well, right, because by saying you're following a geodesic equation, that is saying you are following the principle of least action or something, and you are going to go on the shortest geodesic path. I mean, that's
right, exactly. And so because we have the ability, so in the causal graph case, we have the ability to derive that action principle from purely computational considerations. And all I'm pointing out is I don't think it's that much of a stretch to say that an analogous action principle works for a multi-way system based on metamathematics. And therefore,
let's review that claim. Okay, so what you're saying is that your claim is it's inevitable if you have computationally bounded observers. So the construction of the foliations is computationally bounded. It is inevitable, you claim, that
and you have sufficient irreducibility to get ergodicity.
Right.
Then
that in the large scale limit that things will follow geodesics.
Right. So we know that to be the case for a causal graph. And we haven't proved it yet, but we conjecture it to be the case with multi-way systems as well.
Right. Because that's what we believe that's why we believe the path integral works.
Right. Although that hasn't yet been fully formalized. But so in which case we will get an action principle in the multi-way graph, in the multi-way evolution graph, including presumably therefore the multi-way evolution graph for mathematics, which is also irreducible and whose practitioners are also computationally bounded. So you will also get a geodesic equation there, or an appropriate generalization of it. And what I'm trying to work out is why is the statement that sort of number theory is possible to do without getting caught in undecidability. All I'm asking is why is that not just a statement that mathematicians follow a geodesic equation?
Well, it may be, but let's try to understand that. So, I mean, what you're saying is, let's see. In this meta-mathematical space, we've got this. Let's see. I mean, there are many possible paths in meta-mathematical space. A mathematician is defined rather embarrassingly as something computationally bounded.
Right.
And that must be the thing that forces them to have one path rather than another. Well, there are probably two things. One is the overall structure of the space and the whole computational irreducibility, which implies a certain uniformity to the space. I mean, that's essentially what's happening from that. And the other is the statement that that you can't end up, as you explore the space, your foliations of the space have to be something that isn't too crazy.
Right, exactly. And so in the same way as you can make these kind of slightly ad hoc perturbative arguments for the geodesic equation in GR that said, if you tried to perturb your time-like path in such a way that you would be caught up in some infinite length geodesic between points P and Q, there would be some that foliation would become essentially non-constructible. And so because of your computational boundedness, you would not be able to follow that path. And the same thing presumably is also true in mathematics. That if you were about to be caught up in some undecidable path, that would not be a natural or even possibly constructible foliation for you as a bounded as a boundary observer of that multi-way system.
All right, but let's pull this back again to thermodynamics, because I think there's an analogous statement there. So the statement in thermodynamics is the typical observer. What is the right statement in thermodynamics? I mean, there's again an action principle for thermodynamics you can think of, but the main point is the typical observer how to think about this. That you get what I'm saying? I mean, once again, in thermodynamics, you get weird, hard to explain behavior if you allow yourself to do, elaborate non-coarse graining, elaborate measurement of all the detailed, computation of all the detailed positions of molecules, et cetera, et cetera, et cetera. If you assume that you're not able to do that, you conclude that, so what is the analog of the statement that most practical statements are decidable? What is the analog of that statement in thermodynamics? So I think the analog is most things you want to measure behave in a fairly simple way in thermodynamics. And the reason that that happens is that there are things you could measure that would behave in a very complicated way, but you couldn't measure them because they require something that is more, that isn't computationally bounded to make those measurements. So in other words, if I say the pressure of the gas, assume that does this make sense? So what I'm saying is, given the computational boundedness of the thing I'm measuring, that is, I'm not looking at some very detailed number theoretic combination of positions of molecules. I'm instead just looking at the average pressure of the molecules. Given that I do that, given that I'm looking at the thing, using this computationally bounded approach, the kinds of things that can happen in the gas are going to be computationally quite simple.
Sure.
The things that I conclude. So I think this is the statement. If my measurements are computationally bounded, then my conclusion about what's happening, but then what happens with those measurements is also computationally fairly simple. I think that's the analogous statement.
Right. So there exists a one-to-one correspondence between demons and oracles.
Well, okay, let me understand that claim.
In the sense that a demon is an example of an object in thermodynamics which is able to make a computationally unbounded measurement and therefore to do weird stuff that should not be otherwise possible.
Right. But I mean, the thing I'm saying is...
And an oracle in mathematical logic is something that's also computationally unbounded and is therefore able, for instance, to be witness to infinite length proofs and things that also should otherwise not be possible.
Right. But so the claim that I'm making is, as the observation of a gas by a computationally bounded observer who makes measurements that use the computational boundedness, they measure some quantity m or something, q or something. That quantity q must obey essentially equations which are computationally fairly simple. That's the claim.
Yeah,
whereas,
that's the claim of a geodesic. That they're following a geodesic equation.
Right. That it's a moderately simple equation, not too squiggly. And so the logic is, because they are computationally bounded, the things that, even though the underlying dynamics of the gas is full of irreducibility and full of very complicated things, because they're computationally bounded, they're blind to most of that complexity. And the only thing they can see is this thing that's fairly simple.
And so that's why I made the comment about Maxwell's demon.
Right. So the claim is that in general relativity, that the same thing is happening, that the computationally bounded observer who makes tolerably simple foliations is inevitably, right, has to obey a fairly simple equation of motion. That's the claim. And now, okay, so in the metamathematical case, what is the analog of making a computationally bounded statement about metamathematical space? I mean, in other words, in space-time, we kind of imagine, in thermodynamics, we have an intuitive sense of what it means to make a computationally bounded measurement. It's kind of like we're reducing all these degrees of freedom into this one simple thing we're saying. So I think what it is in mathematics is it's saying there are, for example, you can make statements about, a gazillion different numbers, but you're compressing all those statements into a thing you can write down in a textbook. You're not enumerating every different number and saying, this is what's true for this number, this is what's true for the other number, and so on. Just like in thermodynamics, you're trying to make some statement about this whole collection of molecules. So the claim would be that the reason, the analog is that mathematics is written down in finite textbooks. So that would be the analog of the fact that there's a computationally bounded, that the simple measurement, that is just measuring pressure rather than measuring every molecular position and so on, is the analog of saying mathematics is written down in sort of they're modest size statements that can be fitted in a textbook rather than all the micro details of mathematics. And then the claim would be that if you look at mathematics only at the level of what's written in textbooks, that then it will tend to be the case that the trajectories you follow don't engage with all of those sort of micro details which show irreducibility. Did that make sense?
Well, yeah.
I mean, do you think this is correct? I think this is actually getting somewhere. I think
in the sense of what's written down in textbooks is a model of a particular object in mathematics that's otherwise defined axiomatically.
No, but what I'm saying is, in mathematics, you've got all this infinite mathematical space of theory.
Trust me, I understood what you said, right? So right. You know, a concept like the natural numbers is a reducibility statement. So you don't have to reason about each individual natural number. You can reason about this entire class of things, right? And there's a restricted collection of things for which you can make those reducibility statements. And those are the things which get printed in mathematics textbooks because otherwise the textbooks would be arbitrarily long, right?
Right. But so that then it becomes, so the statement, the logic of all of these things is the observer is computationally bounded. The observer is making these sort of reduced statements about the world. What is not obvious, okay, so this is the part that's not obvious and that you have to prove, but I think we have proved, is that you can preserve reducibility. That is, that having made a reduced statement about the world, that the world doesn't throw in your face computational irreducibility and prevent a reduced statement from still being true. Because it could be the case that
it's not a statement. That's what I'm trying to confirm. It's not a statement that's being reduced. The natural numbers are not a statement.
Well, they're a way of measuring
they're a model.
What's that?
They're a model for a particular axiomatic system.
Fine, in that case, but in the case of
that plays into this whole interpretation that we've been talking about for since last year about models as reference frames, models as constructed.
I understand, but coming back to the thermodynamic case, right? The fact that you can take this gas that's full of molecules doing all their complicated things, you can just say this gas has a certain pressure and temperature. Okay, it could be the case that that's not sufficient. It could be the case that even if you say, I just want to look at pressure and temperature, that there would not be laws that could be stated in terms of pressure and temperature. It could be that things would fragment crazily and that you could end up, just like you would say, oh, I think I can talk about space-time at this continuum limit level, and I can talk about geodesic equations. You could say, no, that's not true. It's like there's infinite turbulence, and you can't, your thing that you thought was a simple geodesic equation, the low-level structure of space-time at 10 to the minus 100 meters will mess it up. But the statement is that doesn't happen.
Right, but that is the statement of computational boundedness of gauge choice, isn't it?
Well, so wait a minute. So what is not obvious is that the forward translation, okay, so once it's computationally bounded at one moment in time, right? The statement is, because of it, and it's related to computational irreducibility and related to the ergodicity assumptions from computational irreducibility, it could be the case, if it wasn't for that ergodicity, it could be the case that you start from this thing that has a simple description, computationally bounded frame, whatever else you want to say.
And it gets destroyed by the evolution of the system. I understand all of that. So again, why is that different to computational boundedness of gauge choice?
Because the gauge choice, the fact that you can get away with computational boundedness of gauge choice, that is a, right? I mean, so by that you mean that at every moment,
gauge choice is computationally bounded.
No, but you can say, let me make a computationally bounded gauge choice, but it might not be consistent.
That's what I said. Yeah, the fact that there exists a consistent computationally bounded.
Okay, fine. But what I'm saying is the non-trivial fact is that given a particular, hypersurface, space like whatever it is, hypersurface, right? Given a particular thing that you define as a moment in time.
Yeah, the Cauchy problem is well posed and that the gauge choice remains bounded. Yes, I agree. That's a non-trivial inference from ergodicity.
Right. But then that statement would be, that's the statement that we're saying is true across all these kinds of systems, right? That it's true across, that's the basic statement. And I'm trying to understand how that applies in the metamathematical case. That's basically saying that so the analogous statement is, in the forward motion of mathematics, if you can describe mathematics in a textbook, you can still describe mathematics in a textbook, even when you prove theorems from the mathematics you already had. Because it might be the case, here's what might happen in mathematics. It might be the case that at some moment, you can summarize the mathematics you care about in a modest-sized textbook. But as you propagate forward to prove things from that, for example, it might no longer be the case that you can summarize the mathematics. There might no longer be a computationally bounded, choice of frame, so to speak. It might be the case that mathematics is fragmented into all these random facts, and you might no longer be able to corral it back together in something which is, which a computationally bounded observer can deal with.
Yes, you might not be able to make a consistent choice of computationally bounded gauge. Yeah.
Right, but the fact that isn't okay. So let's undo what is assumed there. So we have to assume, what is the analog of ergodicity in mathematics? What is the observation of what we believe is molecules randomly bouncing around, right? Mathematicians proving theorems, what is their analog of that sort of ergodicity?
Well, cross-fertilization between mathematical fields.
Ergodic cross-fertilization between mathematical fields, not commonly observed by mathematicians. What's that?
Sure it is. I mean, so the formal notion of weak ergodicity in our systems is easy to state, right? You for any arbitrary hypersurface you pick in a causal graph, net flux of causal edges through that hypersurface averages to 0 in the continuum limit.
Yeah.
So in mathematics, so if we have a multi-way system based on metamathematics, and you have isolatable regions of here's a particular bundle of paths that corresponds to number theory, and here's a particular bundle of paths that corresponds to algebraic geometry, and here's a particular bundle of paths that corresponds to mathematical physics or something, then it is the case that in the infinite limit, ideas from algebraic geometry infiltrate number theory, ideas from number theory infiltrate algebraic geometry, ideas from mathematical physics infiltrate algebraic geometry, and so on. And that's a thing that people comment on a lot as a sort of somehow surprising notion. My claim is I don't think it is particularly surprising. I think it's the analog of the weak ergodicity hypothesis. It's the statement that when you delineate the boundaries between fields, you are defining a hypersurface in the multi-way system. And when you say, oh, isn't it surprising that ideas from geometry end up playing a role in physics and ideas from physics play a role in geometry, you're stating that there exists some flux of causal edges through that hypersurface that averages to 0. Right.
You make this sound obvious. This is a very non-trivial statement about the philosophy of mathematics. I mean, so the claim would be that the progress of mathematics has certain inevitable cross-fertilization. That is,
right. I mean, it's obvious when you think about the contrapositive, right? So if you imagine, so suppose it were the case that you had a particular bundle of multi-way paths that was geometry, and you had a particular bundle of multi-way paths that was algebra or something, and they never communicated. That's obviously a failure of ergodicity, right? Because I can use that information to sculpt a hypersurface in which there is a net flux in a particular direction.
No, I understand that, but I think the main point is all these fields are universal, and that's why all these fields are computation universal, and that's why, in a sense, it's inevitable that a statement in field 1 can be made in field 2. What is, I suppose, not obvious is that, and again, it relates again to this question about, the translation difficulty between universal systems, the extent to which it's, how difficult is it to read in, to have something in geometry read in algebra, for example, right?
Right.
I mean,
it takes a long time for people to figure it out.
Well, yes, right. But I mean, but the fact is that's the mixing time, right? That's the ergodic mixing time, is the time for these fields to interweave. So the statement, this statement that mixing time, the thing that's a little bit surprising is the intuitive impression is that mixing time is on the order of a century for human mathematicians between these fields, right? And yet we're claiming that there is intense enough mixing that it's enough to maintain, to make it be the case that, I mean, the claim would be that if you didn't have that mixing, that you would start getting this fragmentation, that the mixing is what prevents fragmentation. And I suppose that,
just like mixing in causal graphs is what prevents fragmentation of space, right? It's what
indeed
the cohesive geometry for space.
Right. It's what knits space together. So the claim would be that this cross-fertilization of fields is what knits mathematics together.
Right.
And the question is,
it's an interesting point you make. By the way, sorry, I just wanted to pick. So I've never really thought of it that way before, but this point about difficulty of universality proofs basically being an ergodic mixing time question. It's not an intuition I'd had previously, but it's a good point.
Right. But I mean, but in mathematics, I mean, the very fact that we're saying, okay, so one question, which is quite interesting for the philosophy of mathematics, is this statement, there is one mathematics. Right, because that's not obvious. It could be the case that number theory and geometry were just separate things that just went their separate ways. They have different axioms. They just are different, right? But what we're saying from this idea of mixing is that there is, in a sense, one mathematics. Now, by the way, we're also claiming that it is one with physics and one with computational complexity theory, which, is a little bit, but the very fact, so can we even distinguish a mathematics from a physics, for example? I mean, in other words, given this concept of mixing, is it the case that we can say that there's a distinct thing we call mathematics from a distinct thing that we call theoretical computer science? Undoubtedly not. And,
right.
and one...
Not if they're both capable of universality, I would argue.
Well, quite. But I mean, the very fact that, okay, so, but one logical connection is the fact that mathematics can be, okay, so the basic statement here is mathematics can be continued as a finite venture where the textbooks are of bounded length. Because that's not an obvious fact. In other words, it could be the case that as we learn more about mathematics, the textbooks have to get infinitely, get unboundedly longer. Because we just learn more and more and more different things. We're exploring more and more mathematical space. There's more to say in the textbooks. But what is being said is that there exists a choice of frame, effectively, a choice of what you measure in mathematics that keeps the textbooks of bounded length. And the statement that that's possible, one of the implications of what's being said here is the statement that that's possible is somehow related to this mixing idea, which is not what one would have expected. That is to say, is it obvious, to keep the textbooks of mathematics of bounded length? Can that happen even if we make a wall between mathematics and computer science? My guess is no. My guess is that this implies that basically all these areas, in order to maintain that, you have to have this kind of mixing. I think we've had a bunch of interesting comments on this live stream here. Maybe somebody has figured this out with greater clarity than at least
Okay, sorry. Something went wrong with my audio there.
Oh, okay. Let's see. Okay, so Nick is commenting, a pattern matching and replacement, the rules of multi-way system of math. So the hardest part is to form an initial condition. Look, I think the hardest part, again, it's all about measurement, because at the lowest level, what's happening is just this thing that's doing replacement and pattern matching and so on. But we are identifying certain kinds of things to talk about. What we've got in the end is just the system that is doing computation, whether it's in mathematics, whether it's in physics. But we then have a description of that system in terms of the things that we provide our measurements of that system, so to speak. And those measurements are our whole story about how, there's this particular construct in mathematics and implies this other construct and so on. But I mean, I think the interesting point here, which I hadn't maybe internalized properly, is, this idea about bounded length mathematics textbooks. Okay, so how does that relate?
I still just don't understand why we're saying it in terms of mathematics textbooks. There's a much more concrete statement we can make, which is that the gauge is computationally bounded. The models are computationally bounded.
What do you mean by that for mathematics?
The models are computation, that when we construct a model of natural numbers, given the axioms of natural number arithmetic, that the procedure for constructing that model remains bounded.
I'm not quite sure. Okay, so explain a little bit more. I mean, so we've got this proof theoretic thing that's all these multi-way systems, and it's proving all these propositions, and they're all flowing out there.
Right. And so in all of these other systems, the statement that we can make, that we can reduce the internal operations of those multi-way systems down to, say, a finite collection of numbers, is a statement about being able to make a computationally bounded gauge choice, right? So when we do that in causal, you might say, okay, we have a causal graph, there's computational irreducibility. How can we possibly summarize what's going on in, say, a single number? Well, the point is that if we construct inertial frames, we can summarize everything in terms of just the boost, in terms of velocity. If we make hyperbolic frames, we can summarize everything in terms of two numbers, an initial velocity and an acceleration parameter. If we use, alpha driver gauge conditions, it becomes 4 numbers. If we use gamma driver gauge conditions, it becomes 8, and so on. But the point is that for each of these cases where there's a well-defined gauge, we are just reducing all the dynamics of the causal graph to a finite, to a single number or a finite collection of numbers, just like you would in thermodynamics when deriving continuum quantities. Right.
But the non-trivial fact is that given that choice of gauge, given an inertial frame, that the time evolution of things described by inertial frames aren't crazy.
Well, no, the frame is the infinite time version, right? The statement is simply that there exists an inertial frame. That can be defined as a consequence of the well-posedness of the Cauchy problem from data on some initial hypersurface.
Well, you mean that there's an inertial frame and it stays an inertial frame. That there's a consistent.
No, there's no. A frame is a universal, is a global object, right? When we talk about a frame, if you talk about hypersurface, that's a local thing, but a frame is a global thing. So if I take a particular hypersurface and I take its maximal, if I take the union of its maximal future and past Cauchy developments, I get an inertial frame if the initial frame satisfies some flatness properties, and if the dynamics of the causal graph are sufficiently ergodic for that construction to make sense. And the point is that's sort of the relativistic analog of deriving pressure or density or something from a fluid, is we're deriving beta from the dynamics of the causal graph.
Well, in equilibrium, in a fluid, yeah. There's the notion of, yes, the equilibrium properties. You're saying a frame is like stating the equilibrium properties of a fluid.
Right. And because there exist different gauge choices that are all computationally bounded, there exist different collections of variables we can parameterize them by, just as there exist different collections of variables that we can use to describe continuum properties of matter in equilibrium. But the point is that in mathematics, the analogous thing is the construction of a model. The reason being that, what is a model? What it does is you have a model of a particular theory, a particular collection of sentences in some formal language. And what that model does is it makes decidable propositions that were previously undecidable, right? It forces new implications to be possible. So in other words, you're taking a partial order and you're making it more like a total order, which is precisely what a foliation choice does, right? It introduces new orderings where they didn't previously exist because of this definition of some universal time function. So the analogous statement in mathematics is that there exists a model that it is possible to describe with a finite number of, with a finite amount of information.
I understand, but just like the statement, there is an inertial frame, tells you only a little bit about the physical universe. There's more, just saying there's an inertial frame is, saying there exist, integers and they work this way, is in a sense telling you only about a little, it's telling you a version of mathematics that's been simplified.
Sure. Well, these are all coarse grainings, right? And so of course, there are many, many different models of mathematics which have a natural number object which behaves like the natural numbers we think we understand.
Right. But as you try and get more detailed, less like in statistical mechanics, as you try and make more detailed measurements, there will be more things you can say. And what's not obvious is whether those, what the set of possible gauge choices, as you're putting it, is that are consistent with, for which there will still be things you can reasonably say, where the thing won't just fragment and go crazy, right? So in other words, to say, we have particular examples which are computationally very bounded. So the question is, in other words, okay, so this is another way to put it. What possible theories of thermodynamics are there, right? One theory is equilibrium is characterized by pressure and temperature. That's the only one we know, actually. I mean, it's the only one. I mean, maybe there's one in terms of autocorrelation functions of molecules, I'm not sure. But that would be the statement in general relativity. The only thing we know about is the behavior of inertial frames.
Right.
But in fact,
some equivalently simple, maybe hyperbolic frames or something.
Right. But so the issue is in thermodynamics, we've got the pressure temperature description. We don't happen to have any others there. But the claim is there might be other computationally bounded ones that would be preserved by the time evolution of the system, that would not be fragmented to pieces by the time evolution of the system, that would be a valid description. And so in mathematics, I mean, in physics, again, in physics, we've got a similar kind of thing where we say there's a simplified description of let's say space-time, and it works. We don't have to, I'm trying to understand, we're trying to describe space-time. Well, there's a different issue there, which is this whole question about the presence of. Yeah, I'm not really understanding that very well. But in the mathematical case, what's an alternative? Okay, so we've got the general area of number theory. Okay, and we've got one frame is just the integers. I'm not understanding this very well. I mean, what is the progress of mathematics in this model? Is it finding new frames or what? What is the?
Well, there are several different. I mean, I'm sure we've had this discussion before, right? There are several ways in which mathematics progresses. There is sort of formulating new conjectures within an existing theory. There is proving new conjectures within an existing theory, and there is the construction of new theories. And these are all different. They all have different interpretations in this way of thinking, right?
Well, okay, but in terms of, well, there's more to understand here.
Okay. So if I'm just like exploring a particular field, if I'm exploring number theory, this is just kind of arbitrary search in this particular region of the multi-way system that is that defines number theory. And when I'm doing that exploration, I'm following a model of the natural numbers. I'm following a particular foliation choice, but I'm just kind of casting about more or less at random within this region. When I'm doing the kind of more theorem proving type approach, where there's an actual definite goal in mind, I'm still following that foliation. I'm still following the that order relation that's imposed by treating the natural numbers, treating this object as the natural numbers. But this time I have a definite sort of destination in mind. I'm trying to find a particular path that leads to this vertex. Then there's sort of field creation, which is the construction of additional models. I mean, so now you're saying, okay, we've got the space of all possible proofs, all possible theorems in mathematics, and we have different ways of interpreting different different sections of them. And when we invent a new field, what we're doing is we're marking out a particular section and we're defining a model over it. We're defining a gauge over it, and we're not really caring about what goes on outside, right? And so that's a different model I should stop saying model. That's a different way of conceptualizing the progress of mathematics, which is a sort of construction of new reference frames, a construction of new models.
Okay, but that's yet different from the idea that we change the underlying rules for the multi-way system, which is another different idea. I mean, possibly an unnecessary idea. I mean, that is the idea. I mean, that idea is somewhat denied by the idea of universality and rulal space and all these kinds of things. The idea that you need to change the underlying rules.
Right. And so naively you might think, okay, if I'm going to go from group theory to ring theory or something, I have to change the underlying rules. Right, but of course you can't. If you're operating from ZFC or category theory or some other universal foundation, you don't. There are constructions of both things within the multi-way system you've already got, and so then
Right.
it shifts from being a rule switching story to just being a foliation finding story.
Well, but in rulal space, that's what we think basically everything is, and that's the statement that's universality is a statement that it is possible to find in rulal space sort of anything you want to find by just finding a different reference frame.
Right.
And but so this idea of I mean, this way of just saying I'm going to differently coordinatize my sort of rulal multi-way system of all possibilities. I could as well be saying I will change my underlying multi-way system with different rules. That's an equivalent to saying I will pick out particular subparts of the rulal multi-way system.
Right.
So then it is an equivalent statement that to build a new field of mathematics, one possibility is you take a different axiom system, which means you pick out different, which is the equivalent of picking a different underlying rule system in this rulal multi-way thing, or alternatively, you're picking a different frame in the rulal multi-way system. Those are two complementary ways to think about what you're doing, and that's fine.
I mean, well, but when you say axiom system, you mean underlying axiom system, right? When most mathematicians talk about axiom system, that's not really what they mean. The axioms of group theory and the axioms of ring theory are constructible within the axioms of ZFC or something.
Sure.
Right? So in that sense, you can transform between axioms. That's fine, and that's just a rulual transformation, right? But what you're talking about is a more fundamental thing, which is,
doesn't really matter. I mean, you could do it at several levels. I don't think that's a in the claim that what is underneath all of these things. I mean, we're making the sort of meta claim that underneath all these things is essentially pattern matching and substitution. That's the thing we are. And I don't really know thought about in terms of, that is the raw material of everything computational, so to speak. And, it's a little bit, to me, it's a little bit unsettling that seems a bit arbitrary, although I don't know what its alternatives are.
Right.
I mean, obviously it can be reformulated by, essentially compiling it into lots of other kinds of things. Right. I know you have to leave fairly soon, Jonathan. So this was actually this was going to be a little side topic, getting I guess a question here. I mean, this whole issue of how to think about the analogy between thermodynamics, space-time, metamathematics. I still think I have this guess that economics will also fall into this whole story. Richard on live stream points out suggests unification is an alternative to the idea of substitution and pattern matching. Sort of closely related to the whole pattern matching idea.
Well, it's an interesting point, actually, because it's what that's really saying is that you can describe multi-way systems purely in terms of their branch pairs rather than in terms of their evolution edges.
Well, okay, so by unification, what you're saying is you can
Because
It's a
when one has a branch pair in a multi-way system, what does that really say? You have a pair AB. What it's saying is that there exist non-variable subterms with the same most general unifier.
yeah, right.
So a model of computation based on unification. So we generally, when we describe multi-way systems, describe it in terms of their evolution edges. If instead we describe them in terms of their branch pairs, in terms of their ambiguities that occur when non-variable subterms have the same most general unifier, we would get the same object, but it's a different way of.
No, I understand. I'm just trying to think of what that actual duality looks like. What would that be? So you would take every node as a branch pair. And what connects, and the branch pairs, they're just connected by, the branch pairs are the edges in branchial space.
Right, no, I agree. I mean, the branchial graph is a unification description of the multi-way system.
Right, so effectively what this is saying is you are defining evolution by making rules about branchial edges, as opposed to making rules about nodes in the multi-way graph.
Which, by the way, which brings us on beautifully to your whole programming non-deterministic Turing machines topic.
Does it?
Because the whole problem there, right, with wanting to prove universality of something like the 1-2 Turing machine is you need to have some way of setting up computations on branch-like hypersurfaces so that the inputs.
Yeah, that's a good point. That's a good point.
So then the Turing machine computation is a rule, is interpreted as a collection of rules that act on the branchial graph rather than, on the actual tape.
That is a good point. I mean, gosh, have we thought about this? I mean, oh boy. So how would we actually write down the rules directly in branchial space? Do we have a way to do that? In other words, we've got.
I mean, other than the obvious kind of brute force approach of just say, take a region of branchial space, apply the Turing, apply the NDTM rules and see what that evolves to, and then use that to define effectively Wolfram model substitution rules, and then do that. That seems
okay. So here's another question. So if we think about things in terms of the evolution of branchial space, right? What does that mean for quantum mechanics? What's the picture of quantum mechanics, which is a picture not of the evolution of states in the multi-way system, but the evolution of entanglements, basically? What is is there a formulation of quantum mechanics which is asking, where this is a picture where you're not evolving states, which is the Schrodinger picture story? What the heck is this?
So I think actually so the categorical picture is perhaps closer to what's really going on, right? So the Hilbert space picture of quantum mechanics treats states as being fundamental, right? They're rays in Hilbert space acted on by unitary operators, etc. The category theoretic picture of quantum mechanics. I should say, okay, so the states are treated as fundamental, and the processes, the unitary operations that transform between them, are somehow secondary. In categorical quantum mechanics, it's the other way around. The processes are fundamental, the morphisms are fundamental, and the states are somehow just emergent. They're the objects, but you don't really care about them. But in monoidal categories, in addition to being able to compose processes, compose morphisms sequentially, you can also compose them in parallel, right? And so that's what's happening when we get a branch pair. What's happening when you have a branch pair is you've got a process that was sort of single-threaded and now it's become multi-threaded. So in other words, you've got a morphism, but now it's now being written. It's now what was a single morphism is now being described as a monoidal product of a pair of morphisms. And so this purely branchial space picture of quantum evolution is close. It's not quite the same, but it's closer to a category theoretic picture of quantum mechanics where you're only reasoning about the monoidal structure, and you're somehow letting the sequential composition, you're letting that be the emergent thing. Right.
The question is there a Schrodinger equation? So if you were to describe, how would you describe things in terms of entanglements? What is the way of describing, is there a formalism of quantum mechanics which is purely in terms of entanglements? And then what is the evolution operator, which is what we're talking about here? And you're saying that's closer. let's see this. Richard is commenting, anti-unification is also interesting. What is anti-unification?
I have no idea. I haven't heard of this.
The, Richard is commenting, the implemented visualization of our physics project with unification as a hack for enumerating all matches. It's interesting. I don't know. We don't.
Okay. This is the obvious. Yeah. Okay. It's the obvious thing. So it's constructing a generalization common to two given symbolic expressions. So it's exactly the time reversed version of a branch pair.
Okay, so it's the merging. It's a merging event.
Something like that, yes. But perhaps better viewed as being you are going back up rather than coming down. You're going back up a branch pair. It's not that they're merging later on. It's that you're.
Although you could formulate things in terms of them merging later on.
Yeah, sure. And that probably is deeply related to anti-unification. But.
Right. But so, by the way, in the case of mathematics, what is the formulation in terms of, what is this formulation in terms of branch pairs? So in mathematics, a branch pair, I mean, the branch pair is the critical pair lemmas.
Right. It's everyone's least favorite way of thinking about mathematics, which is thinking about mathematics purely in terms of critical pair lemmas.
Yeah, but what is that? What is the intuitive version of that? I mean, it's very bizarre because it's very proof theoretical. I mean, it's very, critical pair lemmas are basically different proof paths. And mathematics, the thinking about mathematics in terms of the equivalence of proofs is a very, very bizarre thing, because mathematicians usually just say, just give me a proof. They don't say, give me a family of proofs and consider the correspondence between them.
In channeling Michael in the previous discussion, this is the distinction between classical and homotopy type theory.
Yes.
Right. So once we're at the level of describing metamathematics in terms of critical pair lemmas, you are kind of inevitably in the domain of homotopy type theory, because you're suddenly saying, we're at this point in metamathematical space. There are proofs that go off in these two directions, but actually there's some fundamental equivalence between them, and that's effectively defining a homotopy between those paths.
Right, but the fact is that mathematics, as normally practiced, textbooks typically have one proof of things in them. And people imagine that mathematics progresses by single proofs. If now we say we're going to consider these multiple proofs and the proof of equivalence between proofs and so on, how does that change? I mean, it is inevitable that there exist these multiple proofs. That's an inevitable feature of mathematics. Mathematics arguably wouldn't work unless, so the metamathematical structure would not be knitted together were it not for the fact that there are multiple proofs. Jonathan just froze, at least for me. Well, we can go on here. I think Jonathan had to leave soon, so we may have we were frozen thinking about the implication of branch pairs in for the knitting together of mathematics. That's a good deeply abstract place to end, I suppose. All right, we're going to need to end soon anyway. So unless that's Jonathan's back.
Sorry. Sorry. No, the last thing I heard was you were saying it's inevitable that there'll exist multiple proofs.
Right. So the issue, and I know you have to go soon, but the issue is that the knitting together of mathematics, the fact that there's coherence in metamathematical space is a consequence, in this setup, of the fact that there are multiple proofs of things. Now, normally in mathematics, the fact that there are multiple proofs of things is thought to be completely irrelevant.
Right. Well, it's not just that there are multiple proofs, but also that it's possible to get between them, right? That there exist homotopies between those paths.
Yes. But so normally in mathematics, it's like, who cares? Right? So
right.
In quantum mechanics, in both relativity and quantum mechanics, this is sort of obviously important because it's what allows you to knit together the structure of space or the structure of branchial space or whatever. And it's sort of necessarily but why in mathematics, why is it the case that this branching, which seems in these models to be critical to knitting together mathematics, why is that obvious? What does it mean to knit together mathematics? I mean, we went through this before, talking about your claim, which where I claim the mixing time is 100 years, which is kind of long on the time scale of mathematics as it's developed so far, of the necessary mixing. So why is the existence of multiple proofs? Why is that a feature of that has to be the case in order to kind of knit mathematics together? Unclear. Well, an exercise for next time. We should probably wrap up. It looks like your internet is is flaking out again. But okay, well, we only got through one topic out of about three here. So, well, to be continued another time. And
sounds good. All right.
All right. See you. Thanks for all right. Thanks, Jonathan. Thank you to everybody on the live stream, and we'll see you again another time.